So last time we have proved this lemma. If A is equal to QB plus R, then GCD of AB is equal to GCD of BR. So this is easy to verify. Consider say A is equal to 27 and B is equal to 4. Now we can write 27 as Q 6 into 4 plus 3. Is it? A is equal to QB plus R, and R is now 3. And here, according to the result, what is GCD of AB? So GCD of 27 and 4, and is equal to GCD of BR. So B here is 4 and R is 3. So which is equal to 1. Both are equal to 1. So that is the meaning of the result. Now we shall consider actually the Euclidean algorithm. Euclidean algorithm is a process to obtain the GCD of two numbers which are bigger, not simple like this. And what we shall consider here is that as because the GCD of A, B and is same as GCD of mod A and mod B, so that means GCD does not affect positive and negative integers. So here GCD of 24 and 7 and 4 is 1. So we also have GCD of minus 24, 27 and 4 is equal to 1, or 27 and minus 4 is also 1, or GCD of minus 27 minus 4 is also 1. So negativity, or if the number is negative or positive, that does not matter for the greatest common divisor. The greatest common divisor remains the same, and therefore we assume here A is greater than or equal to B and both are greater than 0. And applying division algorithm to A and B by applying division algorithm, we have A is equal to the same equation we should write. A is equal to, instead of Q we can consider Q1B plus R1. And here what are the possibility for remainder? 0 is less than or equal to R1 is less than B. Now if R1 is 0, then you see the equation A is equal to Q1B. And this shows that B divides A. So therefore B divides A, and therefore GCD of A and B is B. And we stop here. We get the GCD. Now if R1 is not 0, we continue this. So further, if R1 is not equal to 0, then divide B by R1. So we divide B by R1 to get another set of equation for B. So B is equal to Q2 R1 plus R1. Actually here what we have done is we have divided A by B, and the quotient may be written here is Q, and thus this is BQ and the remainder is Q, quotient is Q1 and the remainder is R1 here. And in this case we have divided B by R1 and the quotient is Q2 and the remainder is R. So that is the second division. And here we shall consider if R2 is 0, then we stop. Then we stop, and in this case we shall get the GCD of B and R1 is R1. But if R2 is not 0, then we continue, and thus we will have a system of equations. we have a system repeating this division process, system of equations as first equation is A is equal to Q1B plus R1. 0 is less than R1 less than B. Now we will not write it equal to R1 because if it is equal to R1 then we stop here. And further the second equation is B is equal to Q2 R1 plus R. And here 0 is less than R2 is less than R1. And next we will divide R1 by R2 and get the next set of equation. Divide R1 means we will have R1. R1 is equal to Q3 R2. We are dividing R1 by R2 and the remainder will be R3. 0 is less than R3 is less than R2. And so on. In general, we will have Rn minus 1 is equal to. Now you see the difference in this. This is a set of equations. If it is 1, then it is 3. So 2 more. So therefore here it will be 2 more means Qn. And R2 that is 1 more means Rn. Plus R3 which is same as Q3 suffix, and therefore this is Rn. So you see this will be Qn. Rn n minus 1 plus 2 more, and this will be 1 more means it is n, and this is Rn plus 1. So 2 more means this will be n plus 1, Qn plus 1 suffix Rn plus, and this is Rn plus 1. And again 0 less than Rn plus 1 is less than Rn. And final equation will be for Rn. If this is the last remainder, then the next last non-zero remainder, that is Rn, and this will be Qn plus 2 Rn plus 1. So thus this is the last set of equations that we shall obtain in this division algorithm process. So see this Rn minus 2 we should consider. We shall correct this. This is Rn minus 2, and last is we shall consider as Rn minus 1. So now you see. So what will be this one? Rn minus 2. We have to increase by 2, and this will be Qn, and this will be Rn minus 1, and plus Rn, and the condition for Rn it will be 0 less than Rn is less than Rn minus 1. And finally the Rn minus 1 will be so this is Qn plus 1. Increase the suffix by Q1, Q2, Q3, Qn plus 1. R1, R2 and so on. Rn minus 1, this will be Rn. And this now is 0. The last remainder is 0. And so there is no need to write here the condition because it is 0. And in this the system of equations, the last non-zero remainder, we shall claim that the last non-zero remainder is the greatest common divisor. Now what are the remainders in this division process? In the first stage, first division, this is second division. In the first division, R1 is the remainder. Second division, R2 is the remainder. Third division, R3 is the remainder. Last but one division, Rn is the remainder. And for last division, 0 is the remainder. So last non-zero remainder is Rn, and that is the GCD. So we claim that GCD is Rn. So in this process, we claim GCD of A and B GCD of AB is equal to Rn, the last non-zero remainder. Now how this can be done? We shall use this lemma for the system of equations. Using the lemma, so using the lemma we have lemma for the system of equations. For the first equation we see GCD of AB. GCD of AB is equal to GCD of, now see, GCD of AB is same as GCD of BR, and here GCD of BR1. Instead of R there is R1. So GCD of BR1, and this is now consider the second equation. GCD of BR1 is same as GCD of R1 and R2. So GCD of AB is same as GCD of BR. So from the second equation, this is equal to GCD of R1 R2, and GCD of R1 R2 will be same as GCD of R2 R3. So this is equal to GCD of R2 R3, and this is continued. So this is equal to continue up to, you see, the last but one, GCD of, and here what we have, GCD of Rn minus 1 and Rn. And again this is equal to GCD of Rn minus 1 and Rn will be equal to GCD of Rn and 0. Last remainder is 0. And what is GCD of Rn and 0? That is Rn. GCD of any non-zero integer with 0 is always the non-zero integer. For example, GCD of 5 and 0 is 5. Because 5 divides 5, 5 divides 0. Every integer divides 0. 0 could not divide any integer, but every integer divides 0. And therefore GCD of any integer and 0 is the non-zero integer. So similarly, GCD of Rn and 0 is Rn. And thus the last non-zero remainder is the GCD. The last non-zero remainder. The GCD of A. This is known as the division algorithm. Not division, but the Euclidean algorithm. Euclidean algorithm to find the greatest common divisor. We have used the lemma to obtain the greatest common divisor. We have a system of equations by division. The process actual solving example is easier, and we will have. But before that, we shall express GCD of AB as a linear combination of A and B. To express GCD of AB as linear combination of A and B. And for this, we can consider the second last equation. Second last means second from last. So this equation from second last equation, we write now we write Rn. Rn is equal, because the GCD is Rn. GCD is Rn. And we write Rn from the second last equation as, take this term on the left side, that is Rn minus 2 minus Qn into Rn minus 1. Similarly, from the earlier equation, replace Rn minus 1. Here will be Rn minus 1. Rn minus 1 in terms of the earlier equations. And go on replacing this in backward direction. We will express finally in terms of A and B. So, continuing this, in backward direction, finally we express Rn in terms of A and B. So there are two parts. First get the GCD and then express the GCD in terms of original integers A and B. Now we shall have an example of this, then this will be clear to you. Now consider example. So this we will consider example from the problem set. Examples. First we shall have the example from the set as find GCD of 306 and 657. Find the greatest common divisor of 307 and 657. Any integers we can consider. This is an example given in the exercise of the book. So we use the division algorithm here first, this process. Now write solution. We use Euclidean algorithm. And the greater number is to be divided by the smaller number. So, and we write this as 657 is greater. So 657 divided by 307. Now see the quotient. Quotient we shall write here instead of here. So the division will be of you can see 2. Divisor will be 2, first divisor, and this is 614. So what is the difference? The difference is here is 3 and 4, 43. And again, now what we have to do is divide 307 by 43. So the same thing we have done here. First A is divided by B, and then the remainder. Then B is divided by the remainder. So what is B? B is this one, 307. So 307 is to be divided by 43. You should check it, and I think it is the same. Now what is the quotient here? The quotient may be of, if you consider 6, then it will be 258. And 258, if you consider what is the difference in this 258 and 307. So 9 will remain, and then from 10, 6, so 49 it will be. So next quotient we have considered as 7, and this is 301, and now you see the difference is 6. Now this 43 we have to divide by 6, and now what is the quotient here? 7, and if you consider this as 42, it will be 1, and then now we have to divide 6 by 1, and now obviously the quotient is 6 and the remainder is 0. Now so what we shall get is now we see 306, it should be 306, not 307, but let it be. So this is one example we have considered, and the last non-zero remainder is 1. So therefore these are the remainders, 43, 6, 1 and 0 are the remainders, and the last non-zero remainder is this one. So 1 is the greatest common divisor of 307 and 657. So we can write the equations like this. Now the first equation will be corresponding to the first division. So we have, or I shall write here, we have first equation 657. 657 is equal to quotient is 2 and 307 and remainder is 43. Next equation 307. This is A is equal to Q1B plus R1. Now next is this 307, that is B. B is equal to 7. 7 into 43 plus 6. And next 43 is equal to, from next division, 43 is equal to 7 into 6 plus what is remaining is 1. And the last is 6 is equal to 6 into 1 plus 0. And these are the remainders you see, 43, 6, 1 and 0. And the last non-zero remainder is 1. So therefore, the GCD is the last non-zero remainder. The last non-zero remainder is the GCD. And therefore, GCD of 307 and 657 is equal to 1. So the last non-zero remainder is 1 and therefore that is the GCD. So this is the procedure used in a Euclidean algorithm. Now see, whatever the integers may be in the book, it is actually 306. We have considered 7, but any integers can be considered. The greater we divide by the smaller and continue this division here. This is the first remainder, take this integer and go on continue. And in this, write these equations also from the first division, second division, third division and so on. The last non-zero remainder is the greatest common divisor. Here it is 1. Now we shall consider the second example. And for the second example, we shall again use Euclidean algorithm. So, problem 2. That is from the book. The problem is to find the values of x and y. Use Euclidean algorithm to obtain integers x and y. Satisfying GCD of 119, 272, and this is 119 times x plus 217 times y. So this is the problem from the book, and now we shall consider its solution. First part we have done as in earlier problem, it is the same. Find the GCD, and the next the GCD is expressed as again the combination of the two integers, given two integers. First we shall consider GCD, right, as a solution. We divide here 272. 272 is greater, and divide 272 by 190. Now obviously the quotient will be 2. So this is 38 and 238, and what is the difference? And see, it is 34. Now again, this is the first process. Now take this integer here, 119, and divide by 34. So now what you may see, the quotient is 3. check it. And this is what is remaining is 7. And so this is 34 into 3. So 102 it is. And now this is 7. Now we take this number here and divide 34 by 17. Now the quotient is 2 and this is 34 itself. So the remainder is 0. When the remainder becomes 0, at certain stage the remainder must be 0, and when the remainder becomes 0, the division process stops. So this is the simple process: divide the greater number by smaller, then take this number here, divide by this remainder, and so on until we get the remainder as 0. And now we have the equations corresponding to this. We write the equations like this: A is equal to Q1B plus R1, and the first equation is 272 is equal to Q is 2, or that is Q1, and this is 119B plus R1 is 34. Next, 119 is equal to 3 into 34 plus this remainder is 7. And now last is 34. 34 is written as 2 into 17. 2 into 17 plus 0. And thus we have these equations. And in this is the R1, R2, R3. And what is the last non-zero? That is 17. So 17 is the GCD of these two integers. The last non-zero remainder is 17. And therefore the GCD of 119 and 272 is equal to 17. So this is the first part to obtain the GCD. Now we are asked to show that this GCD 17 is equal to 119x plus 272 times y. And for that purpose, now we have these equations similar to this. Now to express 17 further as in terms of 119 and 272. Next part. Next, we express 17 as 119x plus 272y. Let's consider the second last equation. From this, we have 17 is equal to, that is this number, GCD. 17 is equal to 119 minus 3 into 34. Now you see, we shall express entirely this as well in terms of 119 and 272. 119 is already there, so only we have to change this and we obtain 272. Further, 34 is to be expressed. First we have expressed 17, now 34. What is 34? 272 minus 2 times 119. So this is, we keep this as it is, 119 minus 3 into bracket. From the first equation, that is 272 minus 2 times 190. Or finally, now we collect 190. So 119, how many terms are there? This is 1, and this minus 3 into minus 2, that is plus 6. 1 plus 6, 7. So it is 7. Plus, how many times 272? 272 is only one term with minus 3. Multiply. And thus we have expressed this as 119x plus 272y, where x is 7 and y is minus 3. So in this way we can obtain first the greatest common divisor of any two integers, and by this Euclidean algorithm process, and then we should use these, write this set of equations from first division, second division, third division, and then consider the remainder as the last non-zero remainder as the GCD. Here it is 17. Now express 17 from the don't use the last equation, last one. 17 in terms of this, then 34 in terms of first equation, and simplify the terms. We shall get this GCD as a linear combination of the original integers 119 and 270. So this is the process of Euclidean algorithm to obtain the greatest common divisor. If the numbers are large or larger, greater numbers, smaller numbers we can obtain directly. So you should solve the remaining problems from the exercise or problem set, and the remaining part we shall continue next time. Thank you.